Okay, we're looking at example 1, section 4.4. I'll probably have to break this up into two videos because there's a lot of parts on this one. We'll get as far as we can until we run out of room. So this is what we need for this problem. We need the derivative of an exponential function with raised to some power. That power is some other function of x up here, so it's not just an x by itself. There's another one on the worksheet that you can see that's just, if you have a base e here, e to the power of g of x. This still holds for that one because if you see the natural log of e is just 1, so that's just a special case really. So we'll use that one as well whenever we see the ones that have e to the x in them. So the one that we're first looking at is here. This one actually does have a base e, so e to the power of 2x. So what this is basically saying, and really the best way to approach these problems where you're asked to find the derivative of an exponential function, is to just, the first thing you're going to want to do is just basically copy it. If it's base e, then you just basically just copy it. If it's base something else, then you're going to put that ln of whatever the base is first. So the first thing that you're always going to want to do is just copy it, e to the 2x, and that's really, you see here that there's the a to the power of gx in the function itself. This is in the derivative. It's the same thing. So you've got a couple of other things here, but that thing is repeated in the derivative. And then this part here, the g prime of x, that's just the derivative of what's up here in the exponent. So in that case, that's just 2, because the derivative of 2x is just 2. That's by the power rule. So what our final answer here is 2e to the power of 2x. Okay, for part B, we get, so this one has a different base. This is z is equal to 5 to the power of t. And just, a couple of, as we do these problems, you can just notice the notation. This is z as a function of t, so its derivative is called dz dt. So it's the derivative of, that thing goes in the numerator, dz, and then whatever variable you see here, that's what goes in the denominator of this Leibniz notation. So here, dz dt, we'll use this thing up here. The first thing we'll want to write is the natural log of a. A in this case is 5. So we get natural log of 5 as the first thing we write. And then again, notice the second thing we write is just copying the function. So that's just 5 to the power of t. Now the thing that's up here is just t itself. So really the g prime is just 1. So we'll just leave it like that. So that's the answer for part B. For C, y is equal to 15e to the 5x squared. So again, this is y as a function of x, so its derivative is called dy dx. And if you've got a number in front, you basically just copy that number. And then again, the thing that you see here, this has base e, so we don't have to worry about that ln part. Ln of e is just 1. So again, notice that the next thing we write is we just copy it. So we get e to the power of 5x squared. And then the last thing we're going to write is the derivative of the thing that's up there in the exponent, which is going to be 10x, again by the power rule. So I'm looking at this thing up here, taking its derivative and multiplying it. That's what the chain rule tells us in this case. Now I can rearrange things so that I combine our constants. 10 times 15, that's 150. And then let's put the x in front, and then we still have that. So there's our final answer. Okay, we could probably fit one more, and then we'll do the rest in the next video. So now we've got w is equal to 7 times 3 to the power of 1 over p. Okay, now one thing just to be very careful with on a problem like this, when you see a number multiplied by an exponential function, be sure that you do not multiply these numbers together first. This is not going to be 21 to the power of 1 over p. Okay, be real careful about that. The reason for that is because it's order of operations. Order of operations says that we have to do, it's PEMDAS, right? P-E-M-D-A-S. The first thing that we want to do is parentheses. There's no parentheses here. The next thing is exponents. Well, there's an exponent right there. Since I don't know what p is, I have to leave this as 3 to the power of 1 over p. If I were to multiply the 7 and the 3, I would be doing multiplication before exponents, and that's violating order of operations. So don't make that mistake. So this is an exponential function times a constant. And again, notice the variables w, and then over here we have a p. So the derivative would be called dw dp. And again, if there's a number in front, we just leave that number. So that's the first thing we'll write. Then we notice this one has a base that's not e, so we'll have to put that ln3. So I'll put times the natural log of the base. That's this part of the formula. I'll put that in parentheses. And then the next thing we do, again, just notice that that's just the exact same thing as the function itself. So I'm just going to copy this 3 to the power of 1 over p. And then I have to multiply by the derivative of the thing that's up here in the exponent. Well, what is that derivative? 1 over p is the same thing as p to the minus 1 power. Let me write that here. 1 over p is the same thing as p to the minus 1 power. So what's the derivative of p to the minus 1 power? Well, you just use the power rule on that. So I'm going to multiply this by, I have to move the negative 1 to the front, so I get negative p. And then I lower the power by 1, so minus 2 power. Okay, so that's the derivative that we have. Let's go ahead and simplify this a little bit. If I've got room here, I think I do. So we'll put this is a negative power, so I'm going to leave that in the denominator. Here I'll just leave this stuff in the numerator. I get 7 ln3 times 3 to the power of 1 over p. And then this is then going to be divided by negative p squared. So there's the final answer for that part D. We'll pick up the rest of them in the next video since we're out of room.